Okay, let's jump right in. There's this huge question hanging over AI research right now. Can reinforcement learning, RL, actually make language models fundamentally smarter? Not just better at regurgitating, but unlocking genuinely new ways of reasoning.
It really is one of the core debates, isn't it? And for a good while, the sentiment in the AI community was, well, pretty skeptical about RL doing that much for LLM's core reasoning.
Yeah, the feeling was more like RL was good for tweaking things, right?
Yeah,
Like making the model better at picking answers it kind of already knew or getting it to sound more like how we want it to.
exactly. More about optimizing sampling efficiency or alignment rather than creating truly new cognitive skills. Like the potential was already baked into the base model, and RL is just a polisher.
But the work we're looking at today, based on the paper and notes you shared, seems to push back on that idea pretty hard.
It does. The authors behind this ProRL method, that's prolonged reinforcement learning, they basically argue, hold on, maybe those earlier studies didn't give RL enough of a chance.
How so? What was potentially limiting?
Well, they suggest two things mainly. One, maybe the RL training was stopped way too soon, like after just a few hundred steps. That might not be enough time for, deeper learning to happen.
Okay, not enough runway. What's the second thing?
The other idea is that maybe researchers focused too much on tasks the models were already pretty decent at, maybe certain kinds of math problems. If the model's already good, you might not see evidence of it learning new tricks, especially in areas where it was initially weak.
Ah, so you wouldn't see the expansion of capabilities if you're only looking where it's already strong. Makes sense. Which brings us to ProRL.
Precisely. ProRL is designed specifically to tackle these limitations. The whole point is to enable extended and, crucially, stable RL training. We're talking 2,000 steps or potentially even more.
Giving it the time and stability needed to actually explore beyond its starting point.
Exactly, to potentially find and develop reasoning strategies that just weren't there before.
So our mission for this deep dive is to really unpack ProRL, understand the technical innovations that allow this prolonged training, and then look at the evidence. Does it actually show LLMs expanding their reasoning in new ways?
That's the plan, to see if the results really challenge that older, more skeptical view of RL's role.
Right, let's get into the weeds a bit then. Making RL stable and effective for thousands of steps sounds non-trivial. What are the key technical pieces here? What's under the hood?
Okay, so at the core, they're not using the standard PPO in its most basic form. They use an algorithm called GRPO, Group Relative Policy Optimization.
GRPO, how's that different?
Well, instead of relying heavily on, say, a separate value function to estimate how good things are, GRPO looks at a group of generated responses within a batch. It compares them to each other to figure out which ones are relatively better. This can give you a more stable baseline for updates, especially when your rewards are a bit sparse or noisy, which often happens in complex reasoning.
Okay, so GOPO helps with the basic update stability. But you mentioned a big problem with long RL runs, entropy collapse.
Yes. That's a major roadblock for long-term exploration. Entropy collapse is essentially when the model gets, well, too confident. Its output distribution narrows down dramatically.
It just keeps spitting out the same few answers.
Pretty much. It gets really good at maybe one way of solving something, but it stops exploring other possibilities. And if you want the model to learn new reasoning, you absolutely need it to keep exploring. Otherwise, it just gets stuck optimizing what it already found.
Right, exploration dies, learning new things dies. So how does ProRL stop this from happening over potentially thousands of steps? This must be where the real innovation lies.
Absolutely. This is where the academic focus, the core innovation, comes in. They integrate key components from another algorithm called DAPO.
DAPO.
Yeah, decoupled clip and dynamic sampling policy optimization, plus some other stabilization techniques.
Okay, let's break that down. Decoupled clipping. That sounds like a tweak to the PPO objective function, using separate clips.
Exactly. Standard PPO uses one clipping value, epsilon, to limit how much the policy can change, both upwards and downwards. ProRL, borrowing from GAVIO, uses two separate bounds, epsilon low and epsilon high.
And why separate them? What does that buy you?
The key insight is the upper bound, epsilon high. By setting this higher, they enable something called clip higher.
Clip higher sounds like it lets things increase more.
Precisely. It makes it easier for the RL update to actively increase the probability of tokens or sequences that the model initially thought were very unlikely. It directly pushes back against the tendency of RL to just sharpen the peaks and ignore the valleys in the probability distribution.
So it's not just preventing big negative changes, it's actively encouraging the model to reconsider things it previously dismissed. boosting the underdogs, so to speak.
That's a great way to put it. It forces broader exploration by making it easier to uplift the probabilities of less likely, potentially novel paths. It's a direct mechanism to fight entropy collapse.
Oh, okay, that's clever. What about the other part of DPO, dynamic sampling?
Right. So alongside encouraging exploration, you need to make sure the model is learning from the right examples. Dynamic sampling helps here. They basically filter the problems the model trains on.
How does that work?
If the model is already getting a problem right every single time, or if it's failing every single time, those examples might get sampled less often.
Why is that? Wouldn't you want it to practice?
Well, if it always succeeds, the RL algorithm doesn't really get a useful learning signal. The gradient is basically zero. If it always fails, the signal can be really noisy or unhelpful. By focusing more on problems where the model has, intermediate success.
The ones it sometimes gets right.
Exactly, the sweet spot of difficulty. That ensures the model gets meaningful feedback, keeps it challenged, and prevents it from just getting stuck or giving up on harder stuff. It keeps the learning signal diverse and effective.
Okay, so decoupled clipping pushes exploration, dynamic sampling focuses the learning, but still, thousands of steps. Things can drift. How do they maintain stability and keep improvement going over that long haul?
This is where the next key technical piece comes in. KL regularization, combined with something really crucial for the prolonged part, reference policy resetting.
KL regularization, right. That's about keeping the current policy somewhat similar to a reference policy, measuring the difference.
It penalizes the model if its current strategy, the online policy, drifts too far from a reference point. This acts as a really important stabilizer, prevents the model from suddenly forgetting everything it knew, catastrophic forgetting, and helps maintain some baseline entropy. They note it's useful even though some other work had dropped it, especially when starting from a decent base model.
But here's the thing. If the model is successfully learning and exploring new strategies over thousands of steps, won't it naturally move quite far away from its initial starting point or even a fixed reference?
Yes, absolutely.
And wouldn't that KL penalty then become huge, eventually overpowering the actual reward signal and basically stopping further learning?
That is exactly the problem they solve with the reference policy reset. This seems to be the linchpin for making the training truly prolonged. They don't keep the reference policy fixed forever.
They update it?
Periodically, yes. They perform a hard reset. They take a snapshot of the current, improved online policy, and make that the new reference policy. They also reset the optimizer states at the same time.
So the anchor point moves with the ship in a way. The baseline for stability catches up to the model's current improved state.
Precisely. It stops that KL penalty from growing uncontrollably and choking off learning. It gives the model a fresh start, regularization-wise, allowing it to keep exploring and improving based on where it currently is, rather than being tethered to its distant past. This reset mechanism is what really seems to enable continuous improvement over those very long training horizons.
That makes a lot of sense. It feels like the missing piece for really extending RL training effectively. It's not just about starting the journey, but allowing the journey to continue.
It seems critical. And the source mentions they actually use multiple sequential training stages, sometimes triggering these resets when they see performance start to level off or even dip, suggesting it's an active part of managing the long training process.
Okay, so they have this sophisticated training recipe. What kind of challenges did they throw at it? Was it just math again?
No, definitely not. And they really emphasize the diversity. They built a big data set, around 136,000 problems covering 5 different areas: math, coding, STEM reasoning, logical puzzles, and instruction following.
A broad spectrum.
And crucially,
These tasks had verifiable rewards. You could objectively tell if the answer is right or wrong, which avoids the whole messy business of trying to train a separate reward model, which it can have its own biases.
got it. Clean reward signals across diverse tasks, and they really did run it for a long time. Oh yeah, the prolonged part is backed by compute figures, something like 16,000 GPU hours on H100s. This wasn't just a quick tune-up. It was a serious extended training effort. They also mentioned things like increasing context windows during training and using reward shaping to discourage endless outputs, all part of the toolkit for making this long-run work.
16,000 GPU hours. Wow. Okay, so let's get to the payoff. What model emerged from this process, and did it actually perform?
The model is called Nemotron Research Reasoning Quen-1.5b. It's a 1.5 billion parameter model, so, not huge by today's standards, but the authors make a pretty bold claim for it.
Which is?
They state it's the world's best 1.5b reasoning model, based on their tests.
Best 1.5B, that's saying something, especially with 70B models out there. What are the numbers? How much better did it get?
The gains compared to the base CAN 1.5B model are pretty substantial, especially looking at pass at 1 accuracy, getting it right first try. On average, they saw like plus 14.7% in math, nearly plus 14% in coding, but get this, plus 54.8% on logic puzzles. Huge jump there. Also, plus 25% in STEM and plus 18% in instruction following.
Wow, over 50% improvement on logic puzzles is dramatic. And you're saying this puts it in league with bigger models?
Yeah, the source notes that these results mean it matches or even beats several 7B parameter models on these kinds of reasoning benchmarks.
Okay, impressive performance uplift. And here's the core question again. Is this just the model getting way better at finding solutions it could potentially find before? Or is it evidence of new reasoning abilities emerging? What analysis do they do to support the new reasoning claim?
Right. This is where they dig deeper than just the headline numbers. One of the most interesting findings, I think, is about the relationship between how good the model started and how much it gained.
Okay. What did they find?
They found a pretty clear negative correlation. Tasks where the base model was initially weak, measured by pass at 128, which gives it lots of tries, kind of measuring its underlying potential. Those tasks saw the biggest performance jumps after ProRL training.
And tasks where the base model was already strong.
Much smaller gains, sometimes even slightly negative gains.
Huh. So it improved most where it was weakest.
Exactly. And the authors interpret this as strong evidence for expanding the reasoning boundary. If RL just sharpened existing skills, you'd expect the biggest gains where it was already good. But seeing the biggest improvements on the initially hard tasks suggests RL is actually building new capabilities in those weaker areas.
That does feel like a powerful argument. It's not just optimizing the known, it's conquering the unknown, relatively speaking. Any other evidence?
Yeah, they also looked at something they called a creativity index. It's basically a metric trying to measure how novel the model's solutions are compared to patterns it likely saw during pre-training.
How out of the box the answers are.
Kind of, yeah. And they found that the prolonged RL training led to a higher average creativity index. This suggests the model isn't just remixing pre-training data, it's actually generating solution paths that are measurably more novel.
Interesting. Did they track performance during the long training run? Did it just keep going up?
They saw different patterns. Sometimes performance plateaued, sometimes it even dipped a bit in certain metrics, diminish, maybe losing some breadth. But critically, on the complex tasks like coding, they saw what they called sustained gains. Performance kept improving throughout the prolonged training.
Which supports the idea that you need that extended time for the hard stuff.
Exactly. It's direct evidence that prolonged training is doing something meaningful for expanding capabilities on challenging problems.
Okay, what about generalization? Did these supposed new abilities transfer to things the model hadn't seen during ProRL training?
This is another really compelling part. They tested it on out-of-distribution tasks, problems different from the training set. One example they give is BoxNet. The base model apparently had zero ability on this task, 0% pass rate. Couldn't solve it at all.
Okay. And the ProRL model?
The ProRL model showed significant ability. It could actually solve the BoxNet problems. Going from literally zero capability to being able to solve a novel pass type, that's hard to explain as just optimization. It really looks like an expanded boundary.
Yeah, 0 to non-zero is a qualitative leap. What about harder versions of tasks it was trained on?
They looked at that too. For instance, graph color problems.
Yeah.
But with more nodes than it saw in training. The ProRL model maintained much higher accuracy as the difficulty scaled up compared to the base model.
Suggesting it learned the underlying principle, not just memorizing small examples.
That's the interpretation, yes. It seems to have developed a more robust, abstract understanding that could generalize.
Any other striking examples?
There's one more visualization that's quite powerful. They looked at the distribution of pass at 1 accuracy across many runs of a specific task, like one called family relationships requiring logical deduction.
And the picture showed.
For the base model, the distribution graph was piled up at 0 accuracy. It failed almost all the time. After ProRL, the whole distribution shifted dramatically. The peak moved all the way over to perfect accuracy.
Wow. Not just getting a few more right, but fundamentally shifting from mostly failing to mostly succeeding.
Exactly. It visually demonstrates the unlocking of a capability, not just incremental improvement. It really makes the case that something new emerged.
So tying it all together, this ProRL work seems to directly address that earlier skepticism, providing specific technical reasons why previous RL attempts might have fallen short, and offering strong evidence that aligns more with, say, how RL works in games like Go, where agents do discover novel strategies.
It positions itself as a counterpoint, suggesting that potential was there but needed the right methodology, specifically prolonged, stable training with techniques designed for exploration and continuous learning to be realized.
It's compelling, but no research is perfect. What limitations did the authors acknowledge?
The big one is definitely the compute cost. That 16,000 H100 hours figure, that's substantial. It makes this kind of training inaccessible for many.
Right, the resource barrier. Anything else?
They also mention uncertainty about how well these exact techniques will scale to truly massive models, like hundreds of billions of parameters. The dynamics might change. The training itself is more complex to manage with the resets and stages.
And generalization, even with the good results.
Yeah, they're careful to say that while the 5 domains are diverse, it's still finite. It showed good O generalization on the tasks they tested, but you can't guarantee it'll generalize to every possible unseen reasoning challenge.
Okay, stepping back to the bigger picture. What are the potential implications, societal impacts, if we accept that even smaller models like this 1.5b parameter, one can be trained to achieve really advanced, possibly novel reasoning?
It definitely cuts both ways. On the plus side, having powerful reasoning in smaller models is great for democratization. They're cheaper, use less energy, potentially run locally on devices or on-premise for privacy-sensitive stuff like medicine or finance. Real-time assistants get better. And, the potential for eventually reaching superhuman reasoning to solve big problems is, well, profound.
But the flip side?
The high compute needed to train them could actually worsen the gap between well-resourced labs and everyone else. And of course, more powerful reasoning capabilities, especially if they emerge in ways we don't fully anticipate, could be misused. There's a real need for ongoing monitoring, safety research, value alignment that keeps pace.
Enhanced capability needs enhanced caution.
Absolutely. The authors themselves stress combining these methods with robust safety and evaluation protocols.
This has been a really illuminating deep dive. It definitely shifts the conversation around RL and LLMs.
It really does. ProRL presents a strong case, both technically and empirically, that if you give RL enough time and the right tools like the decoupled clipping, the KL regularization, and especially those reference policy resets, it can do more than just optimize. It seems it can genuinely foster new reasoning patterns and expand what these models can do, particularly on the hard stuff.
Well, thank you for breaking down this complex but really important study for us and for you listening. It changes the perspective.
My pleasure. It's fascinating work, pushing the boundaries of what we thought was possible.
So it leaves you with a thought, doesn't it? If prolonged RL with these specific technical keys can unlock problem-solving methods the base model simply didn't have access to, what else might be hiding in these networks? What other kinds of reasoning or creativity or complex skills are just waiting for the right, perhaps very long, training process to emerge? And maybe more importantly, as we potentially unlock these more powerful, maybe even novel emergent abilities, how do we make sure we understand them well enough to guide them safely and use them for good? Something to chew on after this deep dive.